I will talk about the software in general, introduce it, and also talk about the upcoming release, Quantumol Electron Collision QEC 1, 2. I will first just remind what has already been said about how electron scattering data is important for plasma physics. Then I will briefly introduce the R-matrix method, which is behind our software, show the software, and talk about the theory of vibrational excitation and how it's implemented. Like my colleagues Sebastian and Martin said, it's very important to input correct reactions and have the right data for the reactions. This is an example from an experimental paper about the influence of vibrational temperature on the argon-nitrogen discharge. The graphs shown here show how the concentration of argon and the vibrational temperature and the electron number density are all dependent on each other. So the only thing to take from here is that it's extremely important to include all data correctly, but also vibrational excitation plays an important role and has to be computed properly and included in the data set. This is the list of electron scattering reactions that we are capable of calculating using our software, Quantemol-EC. And there's an overlap with the list that Sebastian showed. So far, in the previous versions of the software, we were able to compute elastic scattering cross-sections, electron excitation, and rotational excitation by electron impact, dissociative electron attachment, ionization and dissociation, and the feature we're including in the new release is vibrational excitation. The theory behind the entire software, the main theory of the electron molecule scattering is so-called R-matrix theory. The very basic idea behind this theory is that you have a system of the n electron molecule and the n plus first incoming electron. And when this incoming electron is close to the molecule and forms n plus one electron system, you can treat all the electrons as indistinguishable in the inner region. When the incoming electron is far away in the so-called outer region, you may use just an approximate radial solution in the effective potential. The two solutions in the inner and outer region are then matched at the boundaries. And the matrix of the coefficients is called the R-matrix, hence the name of the method. Inside of this R-matrix here in the inner region, one is going to solve the time-independent Schrödinger equation with for fixed nuclei for the n plus one electron problem, and using the trial wave function, which includes the target states, the continuum orbitals, and the square integrable functions which form the n plus one electron system orbitals. When solving the problem, you will have the choice of either freezing of the target electrons in the orbitals or allowing some number of electrons to excite between active orbitals. The first method is called static exchange, and it's good for computing elastic scattering collisions, potentially rotational excitation. And the second one is called close coupling. There is a suite of Fortran codes which allows to implement this theory numerically and produce the cross sections. It's called the UQRMOL, or the newer version is called UQRMOL Plus, and it's developed in the groups of Professor Jonathan Tennyson and Jimena Garfinkel and by many collaborators. And what we do at Quantemol, we developed the interface on top of those codes. The previous product we had was called Quantemol-N, and the new one, which we developed and released in 2019, is called Quantemol-EC, QEC. There is a paper by Bridget Cooper, who is going to talk later at all in Atoms, and you can check it for details. Now I want to show how the software actually looks like. You start with setting up the molecule. You can either open an example or a geometry file, or just add atoms one by one. This is a water molecule I have here. Then the symmetry of the molecule will be automatically detected by a mole probe, which is running in the back end. You can choose the type of orbitals you will be using. This picture shows the molecule inside of the R matrix here. You're free to pick the energy grid you need. And the last panel is just the processes that you are interested in. So here we have ticked elastic scattering, electronic excitation, ionization, and a number of other processes. I will not run it now, but I will show the results from a pre-run example. Yeah, so you'll get data files which can be used later in a simulation, and you also get graphical results which you can plot as you wish. And this is excited states, and you have the data sheet with all the setup and output data. So now the new feature that we're introducing in the release is vibrational excitation, and we added the code by our customer and collaborator Vyacheslav Kokoouline from the University of Central Florida. Vyacheslav has been using Quantemol-N, and now he's using Quantemol-EC to produce the data he needed further for vibrational excitation. And what he did is neglecting the rotations and assuming that the changes in geometry are small. He computed the vibrational excitation cross-section using the partial derivatives of the scattering S matrix. Now the S matrix can be built from key matrices, which come as a standard output of running Quantemol-EC. At each geometry stretch or band for each vibrational mode, you can produce those K matrices, arrive to S matrix, and compute the cross-section. This is an example from a paper from Vyacheslav. It is actually not only about vibrational excitation, but also dissociative recombination for BF3+. So the group varied basis sets to arrive to better accuracy and consider different vibrational modes, stretching, bending, and this is the dissociative recombination. The next examples are already our own, produced with QEC. This is for water, which I showed. The graph shows calculated results for different modes with solid lines, and various experimental and theoretical results with dots and dashed lines. And the agreement is pretty good. I again should note that using the software versus experiment allows to distinguish between different modes. And it is actually important because potentially different vibrational modes can lead to different dissociation channels. This is an example for methane. These are the vibrational excitation cross-sections for different modes and the total cross-section. And just to show that you can compare to results from Quantemol-DB, these are some literature results versus our calculated result. Yeah, you can see the maximum at around 10 eV in both cases. So the model has been developed for systems without resonances, and it has a good agreement for those systems. However, I have tested it for a molecule that does have a resonance, OCS, and the dots show experimental results and the error bars. And the curve shows total vibrational excitation calculated with QEC. Although the result is not as good as for the previous examples I showed, you can see that it can be used as a first step estimator, and the order of magnitude is still pretty good. With this, I want to conclude and say that a trial version of QEC is free and available, and if you're interested, you should just email us and let us know. And thanks for listening.